All right, good morning, everyone. We're going to do 3.3, which is introducing something I don't think you've ever seen before. This is completely brand new. The nice thing is that it is based off of something that we've learned in the past. So this idea of logarithmic functions is actually going to be based off of exponential functions, things that we've studied before. One of the most common is e to the x, and I think we've talked about base e before with exponential growth. Um, so you'll see that come up as we move along. So we're going to kind of jump right into this. You don't have to write this slide at all. But what I want you to look at is kind of what is the idea of where we're headed. And it's all based off of that idea of exponential functions. And today we're studying their inverse. So if I have my original function, which by the way, those of you that'll be moving on to calculus, I usually spend 20 minutes going over this saying, hey, you should remember this from pre-calc. So this is one of those things that comes up over and over again, and those of you taking pre or calculus see it. So here's what we got. If the red function right now is the graph of e to the x, notice as x goes into the input, that's just going to make this grow exponentially, and it's going to continue growing on without any bounds, which is going to keep going up and up and up. Well, what happens if I just switch the x and the y? So remember, if I switch x and y, instead of going over 0 up 1, now I go over 1 up 0. If I was to do that for every point on this graph of e to the x, I would be able to graph the inverse. Because if you remember, the inverse function is switching the x and the y's around and then solving. Well, that's kind of basically what we're going to be doing here. But if I was to switch the x and the y around right here, so if I take x and switch it with y, my goal is to get y by itself. And what you guys don't know yet is how do I get rid of a base, an exponent? And that's what this unit is all about. You don't know this, but officially, if I was to try to get rid of the y and solve for y, what I would have to do is take the natural log of both sides. And I know this isn't going to make sense right now, but the natural log and base e, those reduce out, which tells me my inverse function is the natural log of x. Well, that's what this blue graph is. It's the graph of the natural log. And that's going to be one of the things we're introducing today. So you may or may not have seen ln of x before, but that's what we're going to be working with. I do want you to write this slide right here. All right, we are going to recall some important properties that are very, and actually I think I'm going to do this side first. Every single year in calculus, my students struggle remembering these two facts, and that's why we're kind of reviewing them, is I want you to really connect with that this year to remember how this works. So the first one is 4 to the negative second power. How do we evaluate that? Well, first thing is we don't grab our calculator. These are no calculator questions, and we're just looking to rewrite this in a more simple form. Well, the big idea is if you ever see a negative in the exponent, that negative tells us we can rewrite it as a positive exponent. And you were expected to do that in Algebra 1 and Algebra 2. So hopefully you're thinking, ooh, the negative in the exponent is going to bring the entire base down to the denominator, and it's going to raise it to the positive power. So 4 to the negative 1/2 is the exact same thing as 1 over 4 squared, which, if we simplify, ends up being 1/16. All right? So what about a fraction in the exponent? Well, this one, we have to think of it a little differently. I see this as two separate parts. I see it as 5 to the third power, and then the divide by 4 tells me to do something a little bit different. So I'm going to maybe show a little bit more work on this problem, but I'm going to leave the 5/3, and then I'm just going to pull out the 1/4 power. And so a divide by 4 is the same as timesing by. And if I have a power to a power, my rule said you'd multiply. So I didn't change the value, I just changed the appearance of this. But what does that mean? It means 5/3 is going to stay. And then how do we deal with that 1/4? Well, the 1/4, or the divide by 4, is the exact same thing as the 4th root. Okay. Now, this isn't super helpful right now, but let me show you. I'm going to make up a quick example as to how this could be helpful without a calculator. Because still, doing 5 to the 3rd power, that's 125. And then the 4th root of 125, that's not friendly. So this problem here isn't something that we could do without a calculator, but we can change it from one form to another. And this is the radical form to the rational form. But let me show you something that's a little more helpful. What if I told you to take -8 to the 2/3 power? Okay, so if you look at this, you are expected to know what this answer is without a calculator. However, I don't know many people that can just look at this without changing it into the radical form. So the way I look at this is what do we have? We have -8 squared, right? That's the numerator. But then I've got the divide by 3, and you can kind of skip this step here, but the divide by 3 is the same as the 1/3. And a better way to think of the divide by 3 is the cube root, right? So if I take the cube root, I can write it as, oops, I can write it this way, or, now this still doesn't really help me a ton, right? Now it might, because I know that -8 squared is 64, and you might remember what the cube root of 64 is. If you do, then you got it. Cube root of 64 is 4. So notice I took this answer and I went all the way to 4. But I would actually do it one other way. I'll show you that in just a second. Okay. Is you can actually flip the position. It doesn't matter if the 2 is first or the 2 is on the outside. So what if I rewrote it like this? And this is where I find the value in a problem like this. I could take -8 to the 1/3 power first and then square it. So what does that mean? Well, -8 to the 3rd power, or excuse me, 3rd root. I said that wrong. And then I want to square that answer. So I'm dealing with the inner part first. All right. Well, if I want to think of this, this is saying, well, what times itself 3 times gives me -8? And that's -2. This whole interior part turns into -2, and then -2 squared is +4. Notice we got the same answer either way that we did it. So there's 2 ways that you can think of this. All right, just to recap, what did we kind of just talk about? We said we need to recall 2 important pieces from properties of exponents. And the first one is, this is the general rule. If you have a base raised to a negative exponent, you can rewrite that as 1 over the base to the positive exponent. That's what we showed you with this example right here. Okay. Now, actually, that brings up another interesting example. What if I have something like this? What if I have the negative already in the denominator? So I basically make this, put 1 over this. It's the reciprocal of this idea. Now there's 2 ways to think of this. You could rewrite this as 1 over 3 squared, which we know is 1/9. But if I've got a number divided by a fraction, that's the same as, instead of dividing by a fraction, it's the same as timesing by the reciprocal. So notice this overall answer just ends up being 3 squared, or 9. Now, hopefully you're going to be well experienced with this and you're going to go right from here to the answer. All this intermediate stuff, you don't really have to show too much work. Okay, so if it's negative in the denominator, that basically takes it right up top and puts it in the numerator. All right, so that's the first rule that we have to recall. The second one is what happens if I have a fractional exponent. That's what this work down here did. Well, anytime you have a divide by a number, that's the same thing as the root. So here I have a divide by n. So if I divide by n, that's the same as the nth root, and then just a to the numerator is going to stay. So we could write it like this, and we saw sometimes it's helpful to write it this way, or keep in mind, you can also flip the order of these, and you can do the nth root and then raise it to the power of m. And the reason why either one of these work, and that's what I showed you with this example, notice we got the same answer. We got 4 in both ways that we did it. In my mind, it was easier to do -8 to the 1/3 power or the third root. I'm more familiar with this than I was the cube root of 64. So you just kind of try it and see what works for you. And sometimes it's better to go in one form than the other. All right, and there's actually one more rule. I might as well bring this up. It comes up on the next couple slides, but it's this. What is a to the 0 power? Or what is anything to the 0 power? And this is a kind of important piece. Anything to the 0 power is 1. Okay, so we need those rules today to help us work through this idea of logarithms. And I'm going to paint a picture here. Don't write this slide. I just want you to think of it, and because we're going to go through it real quick. If I ask you to find the value of x, actually right now for a number, this first one, I want you to put in your answer in the chat. What's the answer to x right here? Okay. Yep. The answer is 2, right? Why? Now, here's the important part, and this is what we're doing today. So this really kind of hits home. Is my guess is you looked at this and said, okay, well, 3 to what power gives me 9? Well, 3 squared gives me 9, so the x has to be 2. What if I asked you to prove that to me? Right? How do you solve for x? I can't take the square root of both sides. I can't. So that's the question, and that's the part that you actually have ran into in Algebra 1 is, in Algebra 2 is we came across these problems, and the only way we knew how to do them was guess and check, right? What number, so for number 2, what number for x, 2 to what power gives me 32? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this is 2 to the 1, 2, 3, 4, 5. And we know our powers of 2, so kind of through guess and check, we knew the answer here is x has to be 5. And then same thing here, kind of a quick way to do anything with base 10 is how many zeros does it have? If it has 3 zeros, it's 10 to the 3rd power. Y, 10 times 10 times 10 is 1,000. So my question then gets into, What about a problem like this? 3 to the power of x equals 33. Well, let's think of this. What do we know? Well, 3 to the first power is 3. 3 squared is 9. 3 to the third power is 27. And 3 to the fourth power is, what is that, 60? I think that's 81. Okay, now, process of kind of deduction here, 33 is in between 81. So I'm going to guess my answer is going to be 3 point something, right? And it's closer to 27 than it is to 84. So it's going to be closer to a lower one. But the problem is I don't really know. It's 3 point something, right? So all we can do is guess here. And we know that in math, we don't want to just guess and check. We want to get accurate answers. And that's what we're trying to do is what is the process for getting x by itself to find the exact value? Because there is a value for x where 2 to the power of x is equal to 100. But again, what do we know? We know 2 to the fifth is 32. And 2 to the sixth is 64. 2 to the seventh is 128. So then I know my answer for x has to be somewhere between 6 and 7. If you really want to, this is actually kind of efficient. And don't get scared by this, that we're not going to answer problems like this. But this is just saying that the only thing we know right now is x is between 6 and 7. You're not going to write your answers like this, but this is just kind of our educated guess. All right, and then same thing here. I know that 10 squared is 100, and I know that 10 to the third power is 1,000, so I'm thinking that x has to be somewhere between 2 and 3. Okay? That's why I didn't want you to write this down, is because we're actually just setting the stage for how do I solve problems like this so I can find the exact value for x. And that's the introduction of our new section, section 3.3. So if you didn't get this, if you joined late, this is officially section 3.3. Definitely write this down. We are introducing this whole idea of a logarithm. And a logarithm is the inverse of an exponential function. It's what allows us to solve when the variable is in the exponent. Okay, so that last slide we kind of just talked about. We're going to, after the next couple days, we're going to be able to figure out exactly what x is. And to be honest, it's going to require the use of our calculator. But before we do that, we have to learn the format. So you're going to see this in a second, but this is the kind of the notations that I want you to be aware of. We have kind of two types of logs. We have the kind of a regular log function. So it's y equals the log. And then notice this blue b. This is considered a base. And then x is kind of the function. Log is a function. It's like kind of like a sine or a cosine. It's not, you got to be careful because it's not set up the same way, but it is an operation that our calculator will do for us. And then it's important to note that the number that's right here, that blue b, is considered the base of the function. Now, we have two types of logs. We kind of have our regular log, and then we've got something called ln, which this is considered the natural log. And we're going to get into that a little bit more. Officially, I'll show that in a second. We don't write this in here, but this has a natural base e right here. And we're not going to write that in there for this one because we'll see something in just a second. But what happens if there is no log base right here? Okay, so let's go back to the regular log. If I have y equals the log of x and it's blank right here, then you are going to put a 10. A 10 is considered kind of the regular base, it's kind of along the lines of, remember when we took the square root of a number, 16? We never really put the 2 out in front there. We just said that 2 is always assumed to be there. That's the same thing with the 10. If the 10 isn't written there and it just says the log, it's always assumed that it's a base 10. Okay? And then we actually can rewrite the natural log, can be rewritten in the regular form by changing the base to e. So these are equivalent expressions, and you'll see why this is helpful. So we can rewrite the natural log to a regular log, and then we just change the base. Instead of a 10, we make it an e. Okay, so this is just kind of getting us used to how things are set up. We're actually going to talk about the spot of the x and the y. Now keep in mind, x is the input, right? And then y is the output. That's your answer. So if I have an input, I'm going to take the log with a certain base of that input. It's going to give me an answer, y. Same thing with natural log. If I have a natural log of an input, it's going to give me an answer, y. Well, what we want to do is we are not really familiar, because we're just learning it, with this log format. What we're going to do is we're going to change the log format to exponential form. Or if I have an exponent, we're going to change it into log form. And that's the big part for today. So this is the real important piece you want to get down today. All right. Now, I'm going to slightly adjust this. Okay. How do I move from exponential form to log form? Well, we kind of switch the input-output, but the base always stays the same. And that's kind of just an important thought bubble for you guys to kind of keep in your mind. And I think showing you an example really is going to make it worthwhile. Okay? Something like this. And actually, you know what? Let's get rid of the y. And let's say that 3 to some power is 27. Now, I know you hopefully know the answer to x. Okay? But notice how this is an exponential form because we have an exponent. So we want to take this exponential form and we want to change it into the log form. Well, what changes? The base stays the same. So wherever the b is, in this case, my base is the exponent 3. That's going to be the b part of my log. I'm going to call this the log of base 3. And then notice the answer. Some people like to put a box around this, and you'll see why today. So the answer is what goes into the log function. Well, what was our answer in this example? It was 27. And then if we do this, notice the exponent c, or in this case the x, is what the answer of the log becomes. And that's how we're going to be able to isolate x and solve for x right here. So we're going to have to change from exponential form into log form. And then eventually, not today, but I'm going to show you how to use your calculator to actually solve this. And I believe that's Monday, Tuesday work. So our focus today is just, can we switch from exponential form into the log form? And all it is remembering whatever the base is, stays the base. And then basically it's the exponent becomes the answer, and the answer becomes the input. We switched the output and input. Okay. It usually takes a couple examples for students to kind of get the feel for this, and that's what we're going to do today. Is we're going to probably do more examples than are needed, but I think that builds confidence. Okay. So let's just kind of, our goal is I'm going to give you, you can notice every one of these is written in sometimes kind of a weird format, but it's written um, in exponential form. We want to change or write this into log form. And first thing I usually do is identify what's the base. Right, so I'm going to look at the exponents. I've got 7 to the third power. There's my base. On the next one, since I have my highlighter, I'm just going to highlight all these. I've got 10 to the negative second power. Those are my bases. Here I've got 2 to the fourth power, and this isn't written perfectly, but this base is 3. So those are all the bases. They're going to be in the log, the base part of the log. And then all we do is switch the spot of the x's and the y's. So I usually draw a double arrow because we can go from exponential form into log form, but it's the log of the base. And then all we do is take this answer and we switch it. So now it's the input of the function, and the old exponent, the 3, became the answer. And that's as far as we're going to go today. We're not going to evaluate this or anything, but those are equivalent expressions. So I'd like you to try that with these two, or actually these 3, and I'll give you maybe a minute and a half to do this. The only thing I'll tell you on the last one is this entire thing, it's not written clearly, this entire x divided by 10 plus 4, that's all in the exponent. Okay, so let's just kind of go through this quick. We want to turn every single one of these exponential graphs into a log. So I highlighted the base, so that's going to be a log base 10, and then we take the answer. It's always taking the log of the answer, and that has to equal the exponent originally. Now, there's 2 ways to write this problem. You could write it this way, or notice how it's base 10. It is accepted or acceptable to rewrite this without the 10 in the base, because if you don't write it, it's always assumed that there is a 10 here. Okay, so then the next one, it's the log of the base is 2, and that has to equal the answer of 100. I shouldn't say equal, it's the log of the answer has to equal the exponent. Okay, and then for this one, it doesn't matter what the exponent is. If it's kind of crazy like this, it's still the same format, right? The log of the base, 3, has to equal the, or of the answer, has to equal the exponent. And once you are able to do this in your calculator, then notice it's just algebra. This whole log of 1.7 base 3 is going to be a number in your calculator, and then you can subtract 4 and times by 10, and you'll be able to find the exact answer that makes this work. And that's where we're headed. Okay, now I'd like you guys to reverse the order. And you might get stuck on this one, ln of 1. But go ahead and try this. Now I want you to rewrite it in exponential form. So we're basically doing the opposite. So I'll give you a minute to do this one. Okay, so it's important to kind of remember what's the base, right? This is log of base 2. Make that smaller. And this one, we're going to actually do something special because there isn't a base right now, but this one has a special way to approach it. But for any time we have the log, we're going to be able to identify the base pretty easily, right? This is base 2. So to rewrite this, if I keep the base, it's going to be the base of the answer, right? So 2 to the third is equal to whatever we were taking the log of, which is 8. And notice, that's a true expression, right? 2 to the third power is 8. So you're hopefully starting to kind of form this connection between exponential form and log form. But let's look at this one, because this one's a little odd. There's a couple of ways that we can solve this. And after today, I'm going to actually show you a different approach to problems like this. But for right now, we have to keep in mind that if it's written as the natural log, you can rewrite this as the log of 1 with base e. And that's where you get this e to pop up, okay, or your base to appear. So my base is e, and if I now rewrite this, the base of e is equal to the base raised to the answer has to equal whatever we took the log of. Now, notice, that is also a true expression. E to the 0 power is 1. E is just that fancy base. It's a number in our calculator. By the way, e to the first power is equal to 2.71818 ... It just keeps on going. And that was if you remember the formula, the PERT formula, with exponential growth, e was the base. There's a connection to the natural log and this base e. I just want to make sure you're aware that when we say e, that's the same e that we've talked about in Algebra 1 and Algebra 2. All right, so now what do? We take the base. This time it's actually an expression, a binomial, and we raise it to the third power, and that is equal to x. And we could do some algebra and try to solve, but these get kind of nasty, so we're just looking for changing form right now. And this problem is the same as the second one we did. We just have to rewrite this in log form with its own base e. And then we can rewrite it with the base e to the second power is equal to 2x. And that's, part of your homework tonight is just changing from one form to another, just like what we're doing here. Okay, so our goal for the next couple slides then is to introduce some properties. The next two slides are very crucial for your success in calculus as well. So please take really good notes here. We are going to look at some important properties of exponents and then look at how those properties appear as logarithms. And keep in mind, you can always change from an exponential base to a log base or a log base to an exponential base. So I should make this a double arrow because we can go either way. So we're going to look at just some facts that we know, and some of them we just saw. I just want to make sure you are 100% comfortable with them. So we're going to start with the exponential forms because that's basically what you're familiar with. And now we're going to look at how that appears with the log form. But let's start with this one. We've got b to the 0 power. Well, as we saw before, anything to the 0 power is equal to 1. So what if I change this into a log form? How does that property look? Okay. We take the log of the base. So if I have the log of some number b, and we're taking the log of 1, that answer is always equal to 0. So if b was 12, the log of 1 with a base 12 is always equal to 0, which means it doesn't matter what the base is, because if the base is just a number, it's always going to be that number to the 0 power in the exponential form. So your answer is always 1 in the exponential form, which means if you're taking the log of 1, it's always going to be equal to 0 because the change from exponential to logs. Okay. Well, what about this? B to the first power. Well, we usually don't write b to the first power, we just write it as b. Okay. Now, for this one, I'm going to highlight just so we kind of see. Um, we have two b's, and they are the same. B is equal to b, but I just want to notice the position. So what is my base? My base is the green b. And if I change that over, this is the log of base b of the answer here was b, is equal to 1. Well, what does that mean? That means if I ever see the log of a number with the same base, its answer is always 1. And the answer is why? Because think about it in exponential form, right? So quick little example. If I have 13 to the first power, isn't that just equal to 13? Yep. So what if I change that into log form? Log of 13 with a base 13 is equal to 1. So anytime you see the log of a number with the same base, you can kind of think of that as just being 1. And the reason is right here. Okay. Now this one's a little weird, but this is true, right? B to the power of y is equal to itself. In geometry, we call that the reflexive property. But what if I change this to a log form? Watch how this appears, because this is kind of tricky. What if I call this my base? Oops, I want to use green. So let's call this one my base. And then this part right here is my answer. So if I do my change of form from exponential to log, it's going to be the log of the green base, b, of the answer. The answer is b to the power of y. Well, that has to equal y. And there's another property that you're going to actually see a much friendlier way to write this on Monday. But it's kind of saying that if you have the log of a base with the same base, it's almost like the bases and the log reduce each other out, and what's left over is the exponent is equal to the exponent. And then the same thing is true here. If I have, let me get this set up. Hold on. Hold on 1 second. I want to see. I don't think I typed that in right. Okay. Um, you could rewrite this. This one's a little bit different. It's kind of odd. I don't see this one come up a lot, but if we take the base here, so the base, and actually that's why this is over on this side. It's already in log form. What if I rewrite it the other way, right? So what do I have? I want to take my answer and I want to take this base. So I'm going to rewrite it as the base to the power of a log has to equal this value x. So it's basically saying if you see an exponent b to the power of the log of b, it's almost like this log of b and this b reduce out, and you're left with x equals x. And this one's just it's kind of a weird one, but it is a property that we will see come up every so often. Okay, now we did this with exponents and regular logs. The same situation is true with the natural logs. So we're going to make that change here quick. I'm just going to show you what that looks like. All right, now e, just remember e is a base, right? And if we did e to the first power, it's like 2.718 dot dot dot. It's just a number. I think of e in the same lines as pi, right? Pi is also a number that continues on forever. It's a irrational number. So that's what I want you to think of as e is not just a letter, it's an actual number. All right, well, we know that e to the 0 is 1. But what does that look like if I change it into the natural log? Well, the base is e. So we're going to keep that as a base. So it's written as the log of base e is equal to, or I should say the log of base e of the answer is equal to the exponent 0. But we also noted that instead of writing the log of base e, we can just rewrite log base e as ln. And this is basically the part we want to connect with. This is a big fact in calculus. You want to really remember that. The natural log of 1 is 0. And why? It's because e to the 0 is 1. So there's the connection between the two. Okay. Well, what about just e? E to the first power is e. So my base is e. And I'm going to rewrite that as the log of base e of e, that's the answer, is equal to the exponent of 1. Well, notice this goes back to kind of that same property. If you have a log e of the base, if the number and the e are the same, I can't say they reduce out, but it's kind of like that, and it equals 1. Or another way to write it, the natural log of e is equal to 1. And this is also another fact we want you to be very in tune with for calculus. Okay, so what if I have e to the y equals e to the y? This is just a true expression, right? That's what we got to agree on that. This is true. So what if I change it? Well, my base here is e of the answer, which is e to the y, has to equal the exponent y, right? And that looks kind of weird, but what we know is that the natural log, this whole log of base e, can be written as ln. And we know that the natural log of e to the y is equal to y. And this kind of gets to one of the big properties we're going to look at on Monday, is a natural log and an e kind of reduce each other out, so all that's left with is the exponent y. Okay. And then this one should go over here. Okay. Now, there's two ways to kind of rewrite this and think of this, but remember how we always just kind of assume there's a base e here? What I would do first is rewrite just this first side, if my pen can work. Keep hitting the wrong button. There we go. So I'm going to, instead of writing this ln, I'm going to rewrite it as the log of base e of x is equal to the natural log of x. So I'm basically going to do the reverse process here. So I have a base e That's going to remain the base. But then my exponent is the natural log, right? Because it's when I convert it back, what does it show me? It shows me that if I take e to the ln of x, the e and the ln reduce out just like they would reduce out here, and what's left over is x is equal to x. So you're going to really kind of get this one in a couple of days. So if you're watching the video, I forgot to record for these two examples, but the way we do the rest of them is the same. So just make sure you go back and look at those. All right, let's take a look at this. The log of 1/25 base 5. Well, that has to equal an answer, right? And what we're going to do is we're going to change it from log form to exponential form. So the base is 5, and it's the base of 5 of the answer had to give me 1 over 1/25. Well, I have a base 5, and my goal is to turn this fraction into something that has a base 5 so the bases match. So the way my brain works is 1/25 is the same as 5 to the third power, but this is a fraction, so instead of writing this as 1 over 5 to the third power, I'm going to write it as 5 to the negative third power. And then the bases match up, which means the exponents match up. So the answer we're looking for had to be -3. And hopefully you're seeing we're now basically able to evaluate logs because we know the exponential form. So there's some a little bit not trickier ones, they're just ones you got to be aware of. So let's try this one. Here I have the base 2 of the answer gave me 32. Now this you might automatically know the answer, and you might say, oh, well, 5, because 2 to the 5th power is 32. If not, then you might have to break down, if you remember your factor tree, you can just keep dividing this. I'm not going to write this, I'll erase it because it's going to take up too much room. But remember back in geometry, how many 2's go into 32? 1, 2, 3, 4, 5. So you could write that factor tree and just say, well, 32 is the same as 2 to the 5th power. Since the bases are the same, that means the exponents have to be equal as well. So the answer to 32, the log of 32 base 2 is 5. Okay. And then here's kind of an interesting one. This one always kind of stumps kids right away. And you have to, there's a couple ways to think of it, but 23 is the base. So if I change it to exponential form, 23 to some power gave me 1. Well, the only possible answer for that is 0. Right? 0 to the base to 0 power is always 1. So 23 to the 0 power is 1, which means the only way that I can ever get a 1 is if it's 0. Now, you could have just said, well, wait a minute, didn't we show that in the last example? Anytime you take the log of something, it doesn't matter the base. If it's the log of 1, the answer is always 0. So there's a little shortcut if you recognize the properties. And then this one here, you might know the answer already. If you have the same log and the same base, you probably might already know the answer. If not, let's take the base of 5 to the power of the answer has to equal whatever we're taking the log of. Well, the only way that this is true, we can always put a 1 in right here, which means the bases have to be equal. So you have to get a 1 right there. So there are shortcuts, and if you recognize them, use them. If not, change it to exponential form and work through the work we did, and it'll be the same. Okay, go ahead and give these a shot. I'm going to give you, let's say, 3 minutes on it and get as far as you can get. There's some trickier ones, but I want you to think about them. All right, we're going to go over these. I'm not sure if that was too much time or not enough time, but really quick, we're going to change from log form to an exponential form. So the base of 2 to the power of the answer equals 1/2. And then just remember, this is really 2 to the first power. And 1/2 we can do, instead of saying 1/2, that's the same as 2 to the -1, which gives us -1 in the exponent. So the answer to the original statement is -1. Now this one I'm hoping you see, oh, all right, anything that's equal to 1 or a log of 1, with doesn't matter the base, is equal to 0. So you might know that answer right away. In that case, you're done. If not, you're going to have to change it to this, and the only way 10 can turn into a 1 is if the exponent is 0. So don't need to do a ton of work for that one. This one might be a little more challenging just because you might not be familiar with what are the bases of 7. In this case, what I would do is play the divide by 7 game. And I'm looking at how many times does 7 go into 343. In this case, there are 3 7s, so 7 to the third power is what gave me this answer. So the answer of log 343 base 7 is 3. Okay. Once you get good at this, you might say, oh, wait a minute, 9 squared gives me 81, and you might know that answer right away. If not, 9 to some power gave me 81, and you don't have to do more work than that if you don't want to, but 81 is the same as 9 squared, so same base, that means the exponents have to be the same. All right, then we get into these two, and this one's actually a little trickier. So is this one. That's why I kind of left them for the last problems. So what do I have? I have 1/3 is the base. To the power of something gave me 3. Now there's a couple of different thought processes on this. Here's the way I think of it. I need base 3. I could try to get this as a 1/3 base, but I go back and forth on how I approach this. Let me show you one way. What if I take the 1/3 and I rewrite it as this? Because right now there's technically a 1 here, right? So if I change the 1/3 to a base 3, that means there had to be a negative in the exponent. And now I have the same bases, so that means -1 to times something gave me 1. Well, the only thing, if I solve for the box, the only way that would work is if this was -1. So that's one way to do it. Okay? Or you could do it this way. You could say, I've got 1/3 to the power of 3. And if I want to keep the base as 1/3, then instead of writing 3, I could rewrite this as 1/3 to the negative first power. So I'm changing this to a -1/3, but I have to make that the reciprocal, and then it shows that those are the same. So I don't know. I like this way first, but either way works. All right, last problem. So I have a base of 2 to the power of something gave me the square root of 2. Well, I want to get this so it has a base of 2. Well, we know that another way to write the square root is there's always the index number of 2 there. So I can rewrite this has an exponent of 1. So 2 to the first power and then the square root is the same as 2 to the 1/2. And now I have the same base, which means the answer is 1/2. Okay. So those are just some quick things. I know we only got 3 minutes left. I had one more slide, but I'll just show it to you, just so when you see it, you don't get confused. and it was problems like this. So here the directions say write the log as an exponential equation. You do not have to solve. So it's the exact same thing we did. You just look at the base, and then you look at, so don't write this because it's going to go pretty quick, but here's the answer. So if I rewrite this, I'm going to take the exponent base, which is x minus 2, to the power of 4/5, and that has to equal whatever we were taking the log of. So it's the same work, except for now there's algebra expressions instead of just numbers. Okay, so same thing here. Here's my base, x to the third to the power of 9/5, and that has to equal whatever we're taking the log of. Now, eventually, we're going to get into solving these, but that isn't until for a couple days. And we don't need to do these. Ooh, I want to show you just this one right here. This is the one that's kind of tricky. So I'll do this quick. You don't have to write it down. I'll just show you. So what is it? It's a natural log one, which we don't really like the natural log right now. So I'm going to rewrite this as a base e, right? So ln, this part right here, is the same as log of base e. And then this part, I don't like the way it's written right now because that fifth root. So I'm going to rewrite it as 4 e to the fourth, and then the fifth root is the divide by 5. So I just changed this so it says log of base e, and now we can go through that same work. Is e to the power of the answer has to equal whatever we were taking the log of, and now notice the same base, so the box has to equal 4/5. Okay, all the other ones we've done before. This one was just a little extra, little tricky. I hope we did a lot of examples, and maybe some of them were too many. Maybe you got the hang of it and you're good, but that's never a bad thing. So tonight's homework is all about changing from log form to exponential or exponential to log, and then trying to evaluate without using a calculator. Okay. Your homework tonight is 3.3 Deltamath. Submit a screenshot. Just keep in mind, early in the trimester here, if you didn't do the work from Monday, Tuesday, or Wednesday, get that done. Submit it, and then you're staying on track. Don't get behind. I'll be available in my office hours from 1 to 2 o'clock today. Have a great day. Enjoy your work with logarithms.